Yeah, don't tell me. If I run more than 5 minutes, I'm gonna die.
The place where the event horizon will form.
If they're
No
not
rays
in
are bunching up
rotation,
and
then
bunching up.
there's some extra pressure.
Just because of the global structure of the space.
And as far as he's
And
concerned,
it
pressure is
will
motion.
shape, almost as if
Therefore,
That's-
this
that's
is proxy for pressure.
How could it be that there's no surface
He's trying to do pressure.
that appears as this structural horizon?
Remember the event horizon. The event horizon tells the boundary of the
Which he helped do that.
general paths of regional horizon. So if you're very, very far away,
I think that.
you're seeing fewer as the conditions.
Yeah, another minute, okay.
But they usually prefer where the horizon goes from
It'll be a collapse.
right before quantum horizon, people would prefer where the horizon goes from.
If you have enough.
He assumed it was static.
Yeah.
They're called
So
it a
there's a
greatest
slowly
mistake.
darkening horizon.
It's a fantastic study.
Okay, so that's a,
Right?
it seems like a less.
Once you're-
And even in the light of simulation, you see that.
It's amazing.
Two structural horizons eventually form
Yeah. I mean, it's still, we still don't know what the.
forms.
What line?
Yeah, what line it is. Yeah, dark energy.
All right, folks, I think we should start.
We should start.
Yes.
Please.
Please.
So today is a pleasure to have Justin Cavitt with us. He's a graduate student in the philosophy department at Harvard University, and his research focused mostly on mathematical logic, philosophy of mathematics, and philosophy of science. And today we'll be talking about black hole research and data-driven science. So please go ahead.
All right, thank you. Thanks for having me talk here. I've always learned a lot, pretty much every time I've walked into the BHI. Hopefully this will be, another experience of that. So today, I'd like to talk through some things I'm thinking through philosophically, how to appreciate the significance of many of the advances that the people in this room are responsible for in empirical black hole research. So starting out, big picture, philosophy of science, a big question, perhaps the central question, understand the nature and extent of scientific knowledge. What makes it possible for empirical data to provide evidence for scientific claims? How is it that we are gaining such great empirical knowledge of the empirical world? And along the way, I'm appreciating what are the strengths and limitations of providing evidence in a given way. Now, in thinking about these questions, at least I found it's much easier to think about science in a very historical context as opposed to ongoing research. It's easier to examine historical science because we have the benefit of hindsight. For example, it's easy to say with several hundred years of hindsight that Newton's Principia was a turning point in empirical science, that it was the theory of mechanics put forward there that starts to give us great evidence in the celestial realm, that the claims put forward there were the baseline that upon which celestial mechanics was built going forward. But I'm saying that 400 years later, 300 and something, with the benefit of having seen that happen. So, big question is, how do we do this for contemporary science? How should we start asking this question? So for this reason, started to think about trying to isolate what are nice special features of various fields historically. One notion to come to is that of a data-driven science. which I use this term to refer to a field that effectively draws substantial conclusions from empirical data. I take this term from an anecdote told to me once upon a time by historian and philosopher George Smith, who upon giving a talk on seismology that was heavily emphasized in particular in the role of theory in providing evidence there, was approached by someone after who said, I always thought that our field was data-driven, not so theoretical. And his response was, well, this is precisely the point I wanted to make. Hence this data-driven term. Sounds nice. Picture is a science in which new data are straightforwardly used to study the world. Examples, I mentioned seismology, particular seismology after the 1960s, when several advances were made that allow for the extraction of new kinds of data and learning many new features of the internal structure of the world.
Pardon me, Justin, just so I can have a picture in my head, can you give me like a simple canonical example of a science that's not data driven?
So this is going to depend, and I will qualify by saying, of course, I don't know any literature fully, but maybe something like one of the social sciences in which many questions are, in spite of lots of data coming in, many questions are nonetheless somewhat open. You can have.
And they're not posed, right? Justin, is the argument you're making. They're not posed in a way to utilize data.
That's a good point, right? That is a good point. Questions not necessarily posed in a way that data can effectively close them.
Yeah.
And also, there may be some other ingredients missing, even if we've got a nicely posed question. Oftentimes, you can have studies that will, say in psychology, come to one conclusion, an alternative study that comes to another conclusion. It seems that data aren't quite, we're not in a position of data giving us the picture of the world.
Wait, so just to clarify, give an example of social sciences, but if it's natural sciences.
I will say I'm unsure without looking at particular
But I,
cases.
I kind of follow Justin's point. I think there are stages in a discipline where you are not as data driven, right? The maturity as a field moves along. So if you look at astronomy, probably like 1900s was when we really started to become with all the Harvard plates and so on. Real push towards sort of data driven. So that's how I'm interpreting. Justin, I don't want to speak for you, but is that sort of what you're suggesting? Okay.
Yes, perfect.
Stages. Yeah.
Yeah, I do think there's a tendency for something like stages in the development of science. Certainly examples where certain sciences have reached that stage. Whether every natural science has, I don't think I'm qualified to answer without going through and evaluating each one in turn. Which one day maybe I will do. Two examples I give you here. I mentioned seismology a bit and celestial mechanics, which will be my main example for much of this talk, because it's very astrophysically related. In particular, I mean celestial mechanics roughly at least after Laplace, as I will get into. So a couple questions that I hope to attack. Not resolve here, but at least bring forward and start to attack. First, how should one characterize data-driven science? How are we to understand what it's like for science to be data-driven? In particular, given the big picture question, we'd like to, at one point, come to an understanding that would allow us to evaluate contemporary science like this. And a related question, what makes this transition to data-driven science happen? Pointed out, think of science as progressing in stages. How do we get to this stage? So, goals for this talk. Go through an example. Said celestial mechanics, data-driven science, point out some features of the science and various features of its development, and then point out some comparisons and contrasts at the end with contemporary black hole research. So most of the talk, go through a quick rundown of the history of celestial mechanics in 4 rather pertinent phases. First, Ptolemy's Almagest. Second, the era around Copernicus and Tycho. Third, the era of Newton's Principia. And finally, the era of Laplace's treatise on celestial mechanics. So to start out, Ptolemy, of course, famously, in his Almagest, put forward a certain model of our solar system, with which he gave us tables recording the various parameters of the planets and the sun and the moon. This world system starts out with certain assumptions, like that the Earth is at rest, and that the motions we're observing are all primarily circular motions, nothing funky like an ellipse going on here. And if there's anything funky going on at all, you account for it with more circles. Hence the picture of different circles, your primary large orbit, and the epicycles you put on top of it. From these assumptions, Ptolemy arrives at the equant model. By this, I mean the model of the solar system where you have the Earth at the center, everything, of course, going around it. Ptolemy is assuming everything goes around the Earth, but the Earth isn't actually right dead center. There are a couple corrections that need to be made empirically. First, the actual center of the circle has to be pushed off in one direction from the Earth in order to account for the periods of retrograde motion. And second, the point at which the motions, the circular motions appear uniform has to be pushed off, in fact, in the opposite direction. That's to say, the motions are circular, but they're not uniformly circular, they're not constant speed. These all come out of empirical observations. There's an excellent paper by James Evans going through taking contemporary data from Mars and showing how if you start with Ptolemy's assumptions, you'll find yourself adjusting right to his model to get an empirically adequate account of Mars. So from this, we get tables of stars and the planets, everything and its place. It's used for the next few centuries. A great way in which empirical data leveraged to draw some conclusions The question that we should all have, knowing history, is why take them seriously? Given that all of these conclusions will need to be revised in some way, as we know. And there is little answer for this. The assumptions are plausible, but just that. The Earth doesn't seem to rest.
So is it correct to say that Ptolemy's model was like an empirical model, and the circle orbits was just how he like parameterized the data in that, or the observations in that model? Is that like a correct statement?
Yeah. The model is empirical, but the features of the model, namely things like circular motion, geocentrism, they come from plausible assumptions, and that's all they can rest on. There's, however, no way of ruling out any alternatives because, well, alternatives come up. Copernicus and Tycho. Famously, Copernicus puts forward a heliocentric model of the solar system. In this model, we have virtually the same predictions for where the planets should appear on the sky, but a completely different account of what the motions are, what distances are, and so on. On top of that, a further wrench is Tycho Brahe coming and giving his sort of hybrid model, where once again, the Earth is at the center, but all the planets go around the sun, which is going around the Earth. So the basic conclusions of Ptolemaic model now in question. Data alone are not enough to decide here. Moreover, there's the question of the distance to the fixed stars, the background stars against which, of course, we're measuring the motions of the planets. If the Earth is moving, you should also appear to move, stellar parallax, which was not observed until the 19th century. We have yet another underdetermined question here. We don't observe stellar parallax. What to conclude from it? The Copernicans concluded the fixed stars are actually a lot farther away than anyone imagined. Tycho, in contrast, concluded it actually just means the Earth isn't moving.
So it seems like there's only one type of data that the geocentrics would want to consider, and those are the data that confirm their, I guess, ideological hope that the Earth will be at the center of the universe. Would you consider a science data-driven if it only selectively is open to hearing one type of data, but it won't really give due weight to the other parts of empirical data that wouldn't confirm what they ideologically wanted?
So I think the opposite would need to be true. A data-driven science should be one where you're letting the data tell you what the world is like. And so insofar as you can't account for the data, you're definitely far from being data-driven, from using the data to tell you about the world.
So data-driven counts all data equally. It's not skewed to one type of data.
Yeah, it should count it all. But part of the issue here is they are counting the data. They're just inferring different things from it. In this case, whether we can infer something about the Earth's motion or something about distances. The correct inference is underdetermined here, but both sides are taking into account the same data. In this case, the lack of observed parallax. One more point on this case, actually very closely related, is the appearance of new data in the form of telescopic observations. Something first brought into astronomy by Galileo, and which are in fact able to answer one question here. Telescopic observations ruled out the Ptolemaic system. You can observe with a telescope phases of Venus that are outright inconsistent with the Ptolemaic system's account of how Venus and the sun move together. Jumping ahead a bit in history, we have Newton's Principia. Several achievements of the Principia include, well, for one, at this point, the various options for models of the solar system have gotten more complicated. Now, elliptical models with various rules for accounting for positions of planets versus time, whether they be Kepler's area rule or some other construction. And among these, Newton claims to give one set of proposals a special status, namely the three principles we now call Kepler's laws. And part of how this is done is via Newtonian mechanics, our good old friend, Newtonian physics now applied to the study of celestial motions. With this, starting from the Principia onward, physics can now tell us things about what the correct motions are and aren't. Before, had no way to decide between the systems. Now, on the basis of Newtonian theory, we know the Keplerian model is the basic correct model. So in a way, data are telling us more from Newton's Principia onwards than previously. But to flag, there were still gaps, namely the theory of the moon, which Newton tried multiple times and could not get quite right, as well as the theory of Jupiter and Saturn, which always had some kind of persistent inequality, some kind of persistent discrepancy in it. These end up being resolved by the time of
Justin, what was the problem with the moon?
problem in the moon. Newton's account of it, I think, was off by actually quite a bit. And I think this has to do with the baseline that he's trying to use to give a perturbational model. The moon is much more noticeably not Keplerian than the planets. So have to do something to account, at least at first, for both the Earth and the sun upon which to build. And I think the issue is Newton's starting points never really panned out for a better perturbation theory.
In particular, he could never get the librations right. The librations were very far off.
Good, thank you.
And yet, these issues, the issues of the moon, continue to persist, rather complicated. But definitely, Jupiter and Saturn are largely handled by Laplace's celestial mechanics. This late 18th century, early 19th century book puts forward theory of Newtonian gravity, Newtonian mechanics, much more sophisticated way, post Lagrange and Euler. And one of its great accomplishments is the identification of so-called great inequality of Jupiter and Saturn. The big problem that we kept running into there, one of the issues with it being that it's a discrepancy that has a period of about 900 years. What's going on it will take a while to actually observe anything regular happening with it. Pure observation, for a few centuries, not viable to identify it. But Laplace is able to identify it on the basis of gravitation theory. And get this, get a lot of very nice quotes from, especially the preface to volume 3 of the work. This one in particular highlights the importance of theory here. Theory of gravity, which by so many applications has become a means of discovery, as certain as by observation itself. It's made known in him, the observer, several new inequalities in the motions of the heavenly bodies, and enabled him to predict the return of the comet of 1759, whose revolutions are rendered very unequal by the attractions of Jupiter and Saturn. He has been enabled by this means to deduce from observation, as from a rich mine, a great number of important and delicate elements, which without the aid of analysis would have been forever hidden from his view. Here Laplace is emphasizing the ingredient that is letting him really start to leverage data to learn about the orbits, in particular, everything around Jupiter and Saturn. This new element are the advances in the theory of gravity that he's putting forward. Yep.
I'm a little confused about the advancements and how they get labeled. Is it really an advancement in the theory of gravity or an advancement in mathematics? For the difference between Laplace's work and Newton's work, I mean.
That's a good question. In part, it is both. It is very much, a lot of what's going on here is theoretical and very mathematical. In particular, a lot of why this could only happen now and could not happen in Newton's time, advances in the way people use analysis, use calculus beyond Newton's more geometric version. So it is mathematical. It's using mathematics applied to physical theory. In that sense, it's theoretical, physically theoretical. Does answer?
I think so.
So, two upshots I want to bring out. I've been bringing out throughout this whole time, been rather clear. On the one hand, the importance of theoretical advances. Just as in the previous example. In these cases, one of the main things that allowed people to bring celestial mechanics into a position of being more and more data-driven, to a position more and more of being able to take data and start concluding things purely just observing, no new significant ingredients needed. Well, that can only happen once you have the right theory in place. Once you get that put in, from Laplace onward, perturbation theory is more straightforward. Another kind of new ingredient that is not as emphasized here, but shows up. In particular, in the example of ruling out the Ptolemaic theory. It's a new kind of data. We got access to a new kind of information about the world, namely things like the phases of Venus, things that Ptolemy was never going to see. Having the right kind of data in itself allowed people to just immediately answer questions on the basis of data. And so to end quickly, not too quickly, some comparisons and contrasts with black hole research to emphasize. On the one hand, theoretical advances are one thing that are enabling, it seems to me at least, black hole research to become more and more data-driven. Something like numerical relativity. Numerical relativity is crucial in LIGO in order to be able to conclude anything from observations of gravitational waves. We need some kind of modeling. We need some kind of attempt to generate templates. And it's from this that we get the parameter estimation. And as advances here go on, parameter estimation gets better. Better parameters hopefully lead to more astrophysics around populations of black holes. But it seems that a more important kind of advance here is the introduction of new kinds of data. I wrote down here, I only wrote down here gravitational wave astronomy. Clearly, we have a new way to detect black holes, giving us more information about populations of black holes within certain mass ranges. Just as well, imaging gives us a new source of information, things such as a new source of mass measurements. It's of M87 star. A new kind of mass measurement to corroborate the stellar dynamical mass measurement, in contrast to the measurement via gases that was off by quite a bit. Even in observations, say of Sagittarius A star, one of the reasons why able to move forward to go beyond statistical models and get specific orbits via the applications of things like adaptive optics. And seems like these are, in contrast to the examples I brought up earlier, perhaps even more important. New kinds of data are leading to new information. But the question then is, to what extent are these leading all of this to be data-driven? To what extent are we drawing new conclusions and drawing them securely, answering questions decisively? And with that, I will end. Thank you.
All right, Priya, please.
So intriguing. I was curious. So are you distinguishing between data and information?
I don't have a distinction in mind. Do you have one?
No, at the
Mind
end,
here?
it was suggestive as you were closing when you talked about sort of visual imaging data versus computational data versus observational data. It seemed a bit suggestive that talking about data and information being slightly different. So I was just curious.
I'm thinking, I guess I'm speaking very broadly of data as various kinds of empirical information.
Oh.
So thinking about, pardon me. But by the way, y'all, I'm congested and coughing, but I've been tested twice. I just have a sinus infection. I'm safe. So in the 1960s, with the so-called, golden age of global structure and general relativity, people like Penrose and Burroughs and Hawking and Meissner started proving these very powerful and beautiful general results about the structure of singularity, about the existence and singularities, about the structure of black holes, about causal structure. And all of this was being done in the complete absence and lack of anything like data that was driving them forward. So I'm wondering, but the other parts of GR, as we just saw it in the previous talk very beautifully, were being at least trying to make contact with data. And even things related to black holes, people were trying to make contact with data. How do you see, on your view, can we talk about general relativity being a data-driven science, or can we talk about the study of black holes as being a data-driven science, or can we talk about numerical relativity applied to black holes being a data-driven science? How do you carve things up? Because it seems like what Penrose et al. Were doing was very much not data-driven, but at the same time, there were these people like Lyndon Bell and and Martin Rees who were trying to say, no, black hole, these things are at the center of galaxies, they're driving these things we just discovered called quasars. And how does all this stuff fit together?
It's a great question. Yeah, I think it'd be best to speak of something like black hole research as being the data-driven science here, as I don't know if I want to say as opposed to general relativity. Clearly, a lot of the increased data-driven advances here are general relativistic. There's increased emphasis in this era on testing general relativity, for example. But right, that these advances on the very theoretical side, often Penrose stuff, I guess they are kind of just that. They are incredible theoretical advances. So I wouldn't count them, at least insofar as they aren't relevant to anything observational as of that time. I wouldn't count them as being part of something data-driven there. Count relativistic astrophysics of that period as being the increasingly data-driven science.
Oh yeah. So in the examples for the celestial motion that you were giving, is it that it seems like some of them, from my understanding, some of those advances are data-driven and some of them are not. So if I'm interpreting this correctly, particularly I'm thinking about from movement from Laplace, from Newton to Laplace, in my interpretation, that is not data-driven because that's a development in the theory. Would you say that when it comes to scientific development, that therefore there's not really necessarily a segment of it that's data-driven, just more of data-driven techniques, I guess, become more prevalent in the science? Because at the beginning of the talk, you mentioned that it seems like a science becoming data-driven happens as a part of its development. But to me, it seems like it's more of it becomes more relevant rather than there's a part that you really label as data-driven.
So I would call the advances Laplace put forward, advances in making celestial mechanics, more of a data-driven science. That's pointed to in his nice quote. It's those theoretical advances that are allowing him to now mine out new information from the world like a rich mine. They are theoretical advances, but they're theoretical advances that allow us to infer more from the data. So in that way, it actually was a contribution to making celestial mechanics more data-driven, completely a priori sort of one. That said, I do agree that it doesn't need to be the case that every advance is connected to making a science more data-driven. Just talked about the advances in global space-time structure from the 60s, which were, as far as I know, less connected to empirical research directly. Of course, draw a lineage back to Oppenheimer and collapsing stars, but yeah, not every advance needs to be from data. Purely theoretical advance is certainly possible, certainly important and amazing. What I've been focused on are the advances that do lead to new inferences from data. Ramesh.
Yeah, I think you've already made the point. So this question about what did Laplace do, right? So Laplace was data driven in the sense Newton couldn't explain the moon, and they didn't know how to explain some of these orbits, right? What was already known about Jupiter, Saturn, etc. And Laplace recognized that Newton was not sufficiently sophisticated in his perturbation theory. So Laplace introduced a new language, interactions between these minor objects, what do they do, resonances, all that whole lot, the whole framework. So it allowed him to explain the already existing data, right? So in that sense, it was mildly data driven. But what he contributed was theory. But then it opened up a whole data driven field, right? After that, every single astrometric observation was valuable data mined, right? To get information inference. So it's kind of in the boundary there. Whereas Eric's question about what did Penrose and Garrosh do, they were mathematicians. They just said, let's take this theory, literally, where will it take us? And they said, yeah, there's going to be singularities, black holes are real, etc. I would like to think it spurred all the astrophysicists who then, suddenly said, these black hole things are real. It's no longer just,
A mathematical solution.
mathematical with crazy properties. It's actually real. And I think it gave us all confidence to just take these things as real. So it spurred data, but I don't think the work was data driven. Would that be a reasonable summary?
Yeah, I think so. Although I think it took longer than for the astrophysicists to take it on board than you might be suggesting.
But that's our problem.
You had a question, Chuck?
Yeah, a brief question. So I'm a humble observer, right? So I think if there is a middle ground between data-driven advances, maybe there is, and theory advances, where that's what saying. I mean, if you take new data and then have a new framework to understand it, right? That's one thing. Then there's a very rich interplay where you can propose new kinds of observations, right? So you can learn something from the theory and then say, there's a new observation that no one's thought of making yet. And we should go out and do that. And that's really kind of cool. It's very interesting. So can you speak, and that's what we're trying to work on a little bit with some of the work we're doing with the next generation PhD. So can you say something about that? Is there an unholy union between these two?
I think it's the holiest of unions.
I'm not getting ecumenical about it.
But yeah, that is an excellent point. That is yet another aspect of the Laplace quote that I had to excerpt out. There's only so much space on a slide. That quote is itself a rich mind. But yeah, totally agree that one of the aspects that occurs in science that are getting, I would call them more and more data-driven, one of the things that theory does help with is it lets you know that there are new things to look for. And in a way, it lets you discover those things prior to you actually seeing them. And this is largely what happens with celestial mechanics after Laplace. It was famously the discovery of new planets, such as Neptune, but even in more subtle perturbations of the planetary orbits. And in fact, the great inequality itself is an example of this, since it's something no one would ever live to observe. Its period is way too large. Yet, as of publication, Laplace can claim, we've learned this, we have discovered this. The data we have collected by repeatedly looking up at the sky has indeed allowed us to conclude this odd variation in the orbit of Jupiter is there. I think that is an aspect, that is a really important aspect of a data-driven science. And in fact, now I'm thinking might even be the more important aspect of what theory can contribute to such a science. Yeah, thank you. Martin.
Hi, yeah, that was a wonderful talk, Justin. I just want to make a comment which is kind of in the line of what was said by Eric, by Ramesh, and to some extent by Chef as well. So the theoretical advances of the 60s and early 70s, as wonderful as they were, of course, are kind of to the modern viewpoint from a mathematics perspective. There's still a gaping hole between the solutions that we have for black holes and the suspicion that what we're observing are indeed approximators of these solutions, right? And of course, mathematically, the business of the finite state conjecture and weak cosmic censorship and so on and so forth. So I guess what I'm saying here is that we're at the eve of a lot of things that are about to happen, and there are huge problems still to be solved from a mathematical perspective, which for me would take us much closer than some of the early stuff. In particular, two things I have in mind. One is formation of black holes. Right? So there is no mathematical story of how a black hole forms other than very specific results in certain settings or local results that don't really extend and produce a full space-time. It's very possible that in our progression in this journey, we will find new theoretical, things that experimentally we can go out and look for. So this is, coming back to Shep's point. There could be something in formation of black holes that will lead us somewhere. So for instance, just to give you something a bit more concrete, right now, formation of black holes is only locally understood for gravitational waves. So the only way we have of making a black hole, right, mathematically, is to take a wave and to focus it, right? Now in nature, that's nothing like what the physicists or astrophysicists have for black hole formation, right? Where usually people think of a collapsing star, collapsing cloud gas, and so on and so forth. Mathematically, coming up with a framework, a solution, an open set of solutions, which instantiates this astrophysical vision, is a totally open question, right? And it's not even that we're close to solving it, we're very far from solving it. So I think it's a really exciting time. And the other thing, but I'm not going to develop it as far because I don't want to talk for too long, but is merger, right? So mathematically, we have no understanding of how black holes merge and how we can model and give a kind of more or less complete mathematical picture of what happens when two black holes come into collision. There is just nothing even close to the desired state of affairs. So I think that leads to leads to a perspective which is the following, which is that it's about to get a lot better. It's very exciting, but it's also very, very hard.
But Martin, you're being very specific. You're saying that I understand only when I can write it as an absolutely complete mathematical description.
Mm-hmm.
You're throwing away all the numerical work. Those guys think they understand gravitational waves, but you're saying that that's only an incomplete understanding.
I'm saying that the right. I'm saying so. Let's
This is
go
for
back
the merger, for your merger
For the
part.
merger
right,
problem.
for the merger part, right? But also for the formation.
No, but
Formation-
formation is a different story.
Yeah, and there we have Oppenheimer's knife.
Yeah.
But I'm thinking of the merger, right?
Yeah,
You said
it's a
merger.
merger.
Well, just so we're on the same page here, the formation story outside of spherical symmetry is completely open. Right?
Yeah, no, I don't disagree with the points you're making about the merger, that the reconciliation of the mathematical framework with the astrophysical insights or processes that could form a black hole, that reconciliation hasn't happened at all. In fact, there is no real description that comes out of mathematical GR that tells you how you could create that space-time. Fair point. But I think I agree with Ramesh that for mergers, at least, we think that numerical GR people are convinced that they have a starting point, right? And that is a credible.
No, so, okay, so let me, I think there may be some kind of miscommunication. So what I'm saying is that as a mathematician, we have no idea what's going on. And the only people that have a clue are the numerical relativists. So I'm not saying what they're saying is wrong.
But you don't think it's mathematical? I'm just trying to understand.
Yeah, I don't think that's right. I don't think that, I think that once we get more complete understanding of what happens, there could be new signatures that we could go look for in the data.
Fair point.
That's what I think.
Yeah, no, and just to toot our own horn a little bit, and I think that's where the VHI.
It's okay.
VHI
I'm tooting your horn, by the way. That's exactly what I'm saying. You guys have the only horn. That's what I'm saying.
Let me make it more explicit. I think the VHI is really and the EHT project is really the first serious attempt in which there's been a real reconciliation of sort of the mathematical framework, numerical attempts to approximate it, and the real data. I mean, and I think that otherwise astrophysics of black holes has been its own thing, kind of, not very connected, other than using, the Schwarzschild radius for the scale and so on and so forth. So I think this work, at least, I think that's what I see as being kind of very attractive about what VHI is doing. It's kind of a grand reconciliation, which has not been attempted, was not possible too, because Ramesh points out the GR simulations were very important piece that intermediary piece to connect, this sort of work that the math, what you would be appropriately mathematical from your point.
Yeah.
That really hasn't happened, and
Absolutely.
It's not happened for the feeding problem yet, or the feeding of black holes. What's going on with the gas? And
well, let me give you an example of something which I find totally fascinating and that I think could be worked on or it has to be thought about. Is that let's leave merger now. Let's go back to formation. The only mathematical picture we have outside of the Oppenheim-Schneider, outside of things like this, is the focusing of these gravitational waves, right? There's no understanding of what happens to matter when it's being forced into this kind of extreme regime where it's about to form a black hole close to the black hole setting, right? It's in particular, mathematically, it becomes very difficult, right? Because you have the equations of fluid mechanics, which are themselves a whole mathematical problem, and the equations of general relativity themselves a whole problem, which start to now, have an addition of those problems. So in particular, it's not known mathematically what to expect when you push these equations of fluid dynamics into a highly relativistic regime. And for that, the only people that can help us are the people who actually simulate this stuff. So as a mathematician, we just have no idea. We're decades behind you guys in a certain way, at least insofar as those kinds of regimes are concerned.
Eric, last comment.
So this is going to be completely unfair, but I have you on, but I have you here, and I have always been completely baffled by how evidence works. I find it really a really confusing issue. Can you say anything about how it is, like on your view, what is it about a theoretical advance or that makes a part of theory amenable to being data driven, or is it advances in data structure that makes that now makes some theory susceptible to being driven by data? Is it a combination of the two? What has to happen? What has to be in place for that bit to flip and all of a sudden data becomes relevant to driving science?
Yeah, so that is an excellent question. That is one that should be very puzzling. And I think,
I'm puzzled.
I think ultimately I'm going to say things that reveal I'm puzzled as well. But I do think part of why we should be puzzled is, well, it's going to be a combination of the things you brought up and perhaps other things as well. So there are going to be multiple facets. So what's going on? We have data, and the whole problem is, why is it evidence for some given theoretical claim? What is it that enables it to become evidence? What kind of advances do we need in order to make that happen? And at a very basic level, it's because, well, the data don't imply the claim. We don't have a logical implication there, so clearly we need something else to license an inference. We need some way of licensing, of giving us reason to assume, if P then Q, to infer Q from P. Now, what is letting that happen in any particular case? Part of it, I do think, is going to be theoretical. It's only on proper understanding of theory that we're going to be able to derive the conditionals we need. It's going to be things like working out what we were just talking about with mathematical framework. It's going to allow us to derive more subtle signatures in the data. Pointed out also data structuring, agree that there something else that also will help to leverage my celestial mechanics examples once again. We only got the fundamental claim that to some level of precision, planets are being governed by an inverse square centripetal force, given that to some level of precision, they satisfy Kepler's laws out of Newton's Principia. Then you need to know you can structure all of these observations in this way. You need something beyond circles on circles. You need, those are at least two ways in which, yeah, something is allowing us to make this inference. Now, of course, I think another reason it's puzzling is cases where you can make the inference. Well, the whole difficulty was you don't have a logical implication. So whatever is licensing your if P then Q there is going to be perhaps really weak, and you're going to need something to say something about why it's maintained. Something about why it is that you can trust these conclusions you're drawing from your data, even though you know you don't have the complete theoretical picture yet. And what makes that happen is going to, I think, get very parochial.
Thank you.
All right, thanks everybody for a beautiful discussion, and let's thank